Okay, here we've come to assignment 6I. Again, it's using everything that we need to know about the fundamental theorem of calculus, which is just evaluating a definite integral. So you integrate and then you evaluate a b minus a, or the upper bound minus the lower bound. Average value is where your rectangle is equal to your curve. And then I believe we're going to be figuring out this value of c. Again, pay attention to those questions when they're asked. And then the second fundamental theorem of calculus says if I take a derivative and it's equal to the singular upper bound, then you can just replace all of these with just a straight up singular x. And then a net change. A net change is an integral of the rate. So if I need to know what is the change in position, okay, the rate of position is velocity, I would integrate the velocity, and that would tell me a change in position. A net change, which is different than a total distance. Again, we'll talk about that when it comes around. All right, so we begin with just straight up definite integrals. And so we integrate and take the upper bound minus the lower bound. All right, so integral of 1 is x, sine is negative cosine, and this is going from 0 to pi. So the first evaluation is at pi, so let's take a look at our unit circle here. We're going to be needing to know information about 0, which is at 1, 0, and pi, which is at negative 1, 0. And so the first and foremost is the pi version, which would be negative 1, minus the evaluation at 0, which is going to be 0, minus cosine, which is 1. And so this ultimately is going to be pi plus 1 plus 1, so pi plus 2. Okay, this one looks scary, but the few trig identities that you need to know. You need to know that sine squared plus cosine squared is equal to 1, and then you also need to know the manipulations of this. So one of the manipulations would be what happens if I subtract sine squared. So that would be minus sine squared, and notice that 1 minus sine squared is equal to cosine squared. So this is the same thing as saying cosine squared over cosine squared. That is the same thing as saying 1. So the integral of 1 is, in this case, theta, or x. From 0 to pi over 4. Just get a little bit more room here. And so that means we take the upper bound minus the lower bound. All right, what creates a secant squared? That would be a tangent. All right, so we need to know information about negative pi over 6 and pi over 6. So negative pi over 6 is at square root 3 over 2, negative 1/2. And pi over 6 is square root 3 over 2, positive 1/2. Okay, tangent is sine over cosine. Tangent is sine over cosine. So the tangents of these would be, in essence, sine over cosine. All right, so this multiplies up. So this is I'll walk you through it here. 2 square root 3 over 2. That's ultimately what that is. You see that the 2's drop, and you don't want square root 3's on the bottom, so this is going to be square root 3 over 3. Same happens with this other one, but it's a negative, so it'll be negative square root 3 over 3. All right, so back to the question. So we want to know the evaluation at pi over 6, and so that's square root 3 over 3, minus the evaluation at negative pi over 6, so that's negative square root 3 over 3. And so that is a positive 2 root 3 over 3. All right, this question, I'm going to take the 4 out. I'll worry about that later. And here I have a secant tangent, which is a derivative of secant. So secant is the integral. All right, so again, we probably need some unit circle type information going on here. So unit circle time, we need pi over 3, which occurs at 1/2 square root 3 over 2. And we need negative pi over 3, which occurs at 1/2 negative square root 3 over 2. Small in the x, big in the y. And secant is, again, 1 over cosine. Okay, secant is 1 over cosine. So the cosine of these things is 1/2. So the 1 over cosine would be 2 and 2. So this is going to be at the pi over 3. That's the upper one. That'd be 2 minus the negative pi over 3. That is also 2. And so that's going to be 0. This is ultimately 0. All right, so we take the integral e to the x is e to the x, or e to the theta is e to the theta. Sine is negative cosine. This is being evaluated from negative 1 to 1. All right. Oh, I know the trick of this one. Okay. All right. Let's go ahead and plug and chug here. So this is e to the 1 minus cosine to the 1 minus e to the negative 1 minus cosine to the negative 1. And so this answer is going to be e minus 1 over e. But what you might be asking, what the heck happened to these cosines? Right, because these cosines are different. All right, and the answer to this question falls within geometry, or trigonometry, I guess. All right, so if I graph a cosine, this is what a cosine looks like. So every value to the right is equal to the value to the left. So if I say, what is the cosine of 1, it's going to give me a value, and I'm just going to make this up. It's going to be 3 or something. No, I'm sorry. It's 0.75 or something. I don't know. And so that'd be at 1. But what would be the cosine at negative 1? Well, it would also be For instance, 0.75. This is called an even function. And so what happens is, in essence, what we're saying is this. A cosine of a positive value is equal to the same cosine of a negative value. So I'm saying cosine 1 is equal to cosine negative 1. They're the same thing. They're the same thing. So what I'm saying is cosine 1 is equal to the cosine of negative 1. It's the same thing. So breaking that down, I'm just going to write this as the cosine of 1 then, because it's the same thing. So this would be e to the 1 minus cosine of 1 minus e to the negative 1 plus cosine of 1, for instance. And notice that you have a negative cosine plus a cosine. And so ultimately, this will be e to the 1 minus e to the negative 1. Again, a negative exponent can be written as a denominator. And a lot of times when things have an exponent of 1, they just don't write it. All right, number 41, determine the area of this. So this starts at 0 and goes to pi over 2. That's the area that they want. And this graph happens to be a cosine. So cosine goes to a straight up sign, not negative sign on integrals. This goes from 0 to pi over 2. And circle time. Okay, I'm interested at pi over 2 and 0. And so this would be the evaluation at pi over 2, which the sign value is 1, minus the evaluation at 0, which the sign value is 0, thus this is equal to 1. Okay, bounded regions. This is a division of x, so this kind of looks like this kind of picture right here. And we're taking it from positive 1 to e. E is like, what, 2 something? E to the first power is 2.7 something. So we are looking for this area right here. And oh, again, a y of 0, so that cuts. All right, so this is going to be the integral of 1 to e of 4x negative 1. Oh, okay, I didn't know why this is on the problem. Okay, so fancy integrals. We know that sine is negative cosine. We know that cosine is sine. We know that secant squared is tangent. Again, just kind of reverse engineering. We know that secant tangent is secant. Fancy derivatives. We know that e to the x is e to the x. Okay, again, derivative of right is going to be equal to the left. And so, question is, what is the derivative of ln, if you recall? What's the derivative of ln? The derivative of ln is 1 over x. or AKA x to the negative 1. And so what makes my spidey senses tip off that, oh, this is the ln answer, is because this. If I have an integral of a negative 1, and I have to, in essence, add 1, what's negative 1 plus 1? Well, that's a 0. And that kind of worries me. That like makes, you know, the hair on the back of my neck kind of stand up a little bit. So there's something afoot. So usually you add 1 to that exponent no matter what, except for when it becomes a 0, that's a hint. Okay, bubble, bubble, bubble. That's going to be the ln absolute value of x. It's an absolute value. So ln absolute value of x. Okay, so this is introducing us to another fancy derivative, or excuse me, fancy integral. All right, so what I'm going to do is I'm going to take this 4 out, and I'm going to integrate that. So this is going to be the ln absolute value of x from 1 to e to the 1. I don't know if you know, but in ln, what the heck an ln looks like? An ln looks like this. It hugs the axis and then it splits over. And this is when the x is 1. So notice that when x is 1, the y-coordinate is 0. Just take note. So when I evaluate this, this is ln of e minus the ln of 1 a lot going on in this problem. Okay, so ln and e are, they undo each other, so this is going to be equal to 1. And then the ln of 1 is 0. So this, and then multiplying the 4, this is ultimately going to be equal to 4. So we now know a new integral. So we have, when this adds to a 0, that means it's going to be an ln. All right, so again, this is f of x is equal to 1/2 x to the negative 1. Okay, so think of it like that. So they want to know what is the, oh, they want to know what is the average value. That they want to know the rectangle equal to the curve. Okay, so this is going to be the rectangle has a base of 1 to 4, so that would be 4 minus 1. This has a base of 3 times the average value is equal to the area under the curve, which goes from 1 to 4 of, as I said, that was 1/2, 1 to 4 of 1 over x, or x to the negative 1. I'll go x negative 1. Okay, so spidey senses tingle. This is going to be the ln of x, 1 to 4, 1/2, and this is 3fc. All right, so this is going to be the divide by 3, so this is 1/3 with that 1/2. ln of 4 minus ln of 1. And so this is going to be 1/6. ln of 4 is ln of 4. ln of 1 is 0, so this is ln of 4. All right, this is a pretty cool answer. However, if you recall, I think in the previous video, I was kind of breaking down an ln. the idea of an ln is if I have a number ln of b, you can rewrite that as the ln of b to the a. So you can bring that up as an exponent. So the number 4 is 2 to the 2. So you could rewrite that as being 2 ln of 2. ln of 2. So if that's the case, this answer could potentially look like this answer could potentially look like 1/3 ln of 2. I think that's the answer in the book, is 1/3 ln of 2. If you can get to that far, awesome. If not, this is the minimum that you need to have. So that's the average value. Okay, again, average value is I create the rectangle. So the rectangle has a base of pi over 2 minus 0 times the height, which is the average value. And then this is going to be equal to the area under the curve, which is 0 to pi over 2 of cosine x. So the rectangle is equal to the curve. The height of that rectangle is the average value. Is that all that I'm answering? Yeah. So this is pi over 2 f of c, and this is going to be a regular sine from 0 to pi over 2. Unit circle. 0 and pi over 2. Multiply by the reciprocal, so this is 2 over pi. And sine is going to be pi over 2. Sine is 1 minus 0. So this is going to be 2 over pi. Average value. So the rectangle is equal to the curve. Okay, here they want the displacement and the total distance. Okay, so displacement is the same thing as saying net change. Like, so for instance, if I, I start at 0 and I run 1 mile this way, and then I run 2 miles this way, and then I run a mile this way, and then I run a last 2 miles up to here. What is my net change? What is my net change? My net change would be 2 miles. What would my total distance be? My total distance would be 1, 3, 4, 6. My total distance would be 6. So there's a difference between net change, that means the displacement, and a total distance. Okay, and this is referring back to the very last formula that we had on the fundamental theorem of calculus. And so net change in like position, or the net change in really anything, but I think of it as a position. The net change in anything is the integral from time 1 to time 2 of its rate with respect to time. So in essence, the change in position, delta st, is equal to time 1, time 2 of the velocity. And that will say, hey, yeah, you changed 2 miles. Okay, and then I'll teach you how to associate this with total distance. Okay, the displacement and the total distance. So let's start with the displacement. The displacement is the change in position. So net change in position is equal to the integral of its rate. So in this case, this is on the interval from 0 to 3 of Vt. That's the rate of position. And so this is going to be 5 over 2t squared minus 7t from 0 to 3. Okay, so the total displacement is 46.5. Oh, that is a change in position. So a change in position this is a position value. I usually write it as delta ST. Delta means a change in. And so this is given in feet. They love their labels. All right, so the net change is 46 feet. But was that the total distance traveled? And here's what the total distance is. The total distance is very similar to this, but it is going to be the integral of the absolute value of V. So again, velocity determines direction. So if, like, I run to the right, and then I run to the left, and then I run to the right again. All right, I run to the right, I run to the left, and then I run to the right. Okay? What it does is it considers this to be all positive. Where net change considers this to be positive, negative, and then positive. So net change, these kind of like negate each other. And then this would be the net change. Where total distance, this is all positive. Okay, so how do you do that? Like, how do you do that? how do you make an absolute value? So what I do is I take my velocity and I set it equal to 0. And I see that I have an important time occurring at 7 over 5, aka 1.4. Okay, aka 1.4. So what I do is I see, okay, time, velocity, and we're going from 0 to 3 seconds, and I have this important value of 7/5 on here somewhere. And so I see that my velocity lower than 7/5 is going to be negative, and this is positive. So if I need my absolute value of a total distance, all right, again, this is flirting with a concept. If I were to integrate, over this, I would get a negative answer. If I would integrate over this, I would get a positive answer. Somehow I need this to be a positive answer, though, because it's the absolute value. So to do that, what I do, the total distance is going to be equal to, I'm going to integrate not over the entire entire time frame, but I'm going to integrate over 0 to 7 over 5. Now, again, as I said, that's going to give me a negative answer because the velocity is physically under the curve. So what I'm going to do is I'm going to say negative that. So this negative answer is now going to be positive. And then to that, I'm going to enter the rest of the time frame. And the rest of the time frame goes from 7/5 to 3. And this answer is going to be positive of that version. And so it's all good. All right. And I already did the integration. If you really take a look, it's that guy right there. All right, so this first one is going to be negative, and then I'm plugging it into the 5 over 2 t squared minus 7t. That's the integral of velocity. But I'm evaluating it at a different number. So the upper bound is 7 over 5. And I'm putting it into the 5 over 2 t squared minus 7t. And then I do the evaluation at 0, which is 0. So you see how it would have a negative distance, but because of that outside negative, that's now considered to be a positive. Now I evaluate this at 3. Minus the evaluation of 7 over 5, which again was negative 49 over 10. So this total distance is going to be 49 over 10 positive plus 3 over 2 plus 49 over 10. (113 over 10). That tells me that I probably did this first bit wrong. Oh yeah, I did. Yeah, this was 3 over 2. I'm sorry. 3 over 2, which is 1.5. Write it in a different color so you can see it a little bit easier. Yeah, I made a mistake up there. I think I queued the first number. So totally, I traveled 1.5 feet, but in all actuality, I really traveled whatever 113 divided by 10 is. I actually traveled 11.3 feet, but net change, I only traveled 1.5 feet. All right, here we go. One more time, or 2 more times, I guess. So this is velocity. So let's go with the net change, the total displacement. And so this is going to be the integral from 1 to 7 of the velocity. I'm just going to write it like this right now. And so looking up at the velocity, this is going to be 1/4 t to the 4th minus 10 thirds t to the 3rd plus 27 excuse me, as you were 27 over 2 t squared minus 18t. Ugh, gross. 1 to 7. So at 7, I think that comes out to be something. Give me 1 second. I'll come back to this. I think it answers itself if I remember this correctly. 7.5, 8, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, minus evaluation at 1. I think this is where it actually answers itself. It's the same value, but watch this. When I turn this into a fraction, it actually does it this time. So negative 91 over 12 minus negative 91 over 12 tells me that the total net change is 0. So this thing didn't move anywhere. Yeah, right. Yeah, right, it didn't move anywhere. We're more wise than that. All right, so net change is the thing didn't go anywhere. Again, the concept of that idea is this. If I run 1 mile this way and I run 1 mile back, what was my net change? 0 miles. What's the total distance? 2 miles. Okay, now let's go ahead and find that total distance. To do that, I need to, okay, here's a concept that I've kind of been skipping over. It's this. If I want to find an area, I'll draw a quick little picture. All right, and I want to know, in this case, I want to know what is the area from 1 to 7. Now, to get that area from 1 to 7, I could integrate from 1 to 7. I could absolutely do that. But it would also be the same thing as saying, hey, I want to integrate from 1 to 2. And 2 to 4. And 4 to 7. So this is kind of a concept that I kind of been skipping over a little bit. And so this is a concept that is being used. And how it's being used is this. This grand distance is an integral from 0 to 3, which we're finding in the first place. This concept is an integral from 0 to 3. All I'm doing is I'm negating the negative portion of that by turning that negative portion positive. That's all I'm doing. But I'm using the concept of I'm representing a grand integral by breaking it up into smaller integrals. All right, let's find where this velocity is negative. So the velocity is equal to 0. That's kind of above my pay grade, so I'm just going to graph this then. And I'm only interested from 1 to 7. So I'm going to graph a 0 and graph this thing. All right, so I have several zeros. So I get t is equal to, I'm going to find these intersections because I graphed a 0 line. Oh, So I have one intersection at time is equal to 1. That's a 0. Time is equal to 3. And time is equal to 6. So again, we're only interested from 1 to 7. We're only interested from 1 to 7. And so that would be 3 and 6. Okay, 1 is one of the edges. And so at time 2, for instance, plugging that into my velocity, into the velocity, not the derivative, into the velocity, I see that that is positive. Oh shoot, I could have just graphed this thing. Yeah, if this is the graph, what is it between 1 and 3? It's positive. Between 3 and 6, it's negative. From 6 to 7, it's positive. Duh, I could have just physically looked at that graph. I'm an idiot. All right. Okay, so what does that help me with the total distance? Total distance is equal to the integral of the absolute value of velocity over the time frame. So what that means is I start off with a positive distance from 1 to 3, and so because that's positive, I don't have to do anything to it. However, it's a negative distance from 3 to 6, so I'm going to subtract that, so turning this distance ultimately positive. And then lastly, I need to cover the time spans from 6 to 7, which again is positive, so that's all good. So the derivative of, the integral of velocity is given right there. So 1 to 3, I evaluate that at 3. Integrate that at 1. Minus, integrate that at 6. Integrate that at 3. Again, that was negative 9 over 4. And then integrate that at 7. Oh, again, yeah, that was negative 91 over 12. And then integrate that at 6. Again, I already did that. That's negative 18. So that should be your total distance. So let's go ahead and put that together. Negative 9 over 4 minus negative 91 over 12 minus negative 18 plus 9 over 4 essence plus negative 91 over 12 plus 18. Yeah, these are in feet. All right. I have to stop this video. I have to teach a class here coming up pretty quick. I will make a part 2 to this video.